Hello guys, in this video we will see how the continuity equation is derived from the basic law. We know that the continuity equation tells that the mass flow inside a system is equal to the mass flow outside the system. Otherwise, it can accumulate inside the system. The same mass should be leaving out of the system. Otherwise, it should rise the mass of the system itself. We know the one-dimensional continuity equation that tells that mass flow in is equal to mass flow out. Rho 1 A1 V1 is equal to rho 2 A2 V2. Let me explain the step-by-step derivation of this three-dimensional continuity equation. So the concept is the rate of increase of mass in fluid element that is equal to the net rate of flow into the fluid element. As a mass is entering into the fluid element, that will give rise to the mass of this element. Let's consider a cubical element like this. So let's name the walls of that. This is the north wall, this is south and east, west, top and bottom walls. And these are the axes x, y and z axis, and this axis denotes this is the positive of x and this is the negative of x. Similarly, this is the positive of z and this is the negative of the z. This is positive y and negative y. And then these are the dimensions of this element: del x, del y and del z. So the total volume of this element should be del x into del y into del z. Okay, now get into the derivation. So the rate of increase of mass in fluid element is, we know that this is the partial derivative, change in something with respect to time. So here the something is mass. So change in mass with respect to time is expressed in this form. Let me explain clearly. We know that density is equal to mass by volume. That is the general formula we use to calculate the density. So then mass is equal to density into volume, right? So the same has been written here. Mass here, dou by dou t into mass is written here. Mass is written in a way that density into volume. Density is denoted by rho and volume is denoted by del x, del y and del z as I have shown here. And then in these terms, only this rho is a variable and del x, del y and del z are the size of this element and those things are constants. So we have kept that constant in this side and we have taken only the density to the derivative. Let's assume this is equation number 1. And just for illustration, I have taken the same image at a different side. So this is assumed as the center of this element. Since the dimensions of this cube are del x, del y and del z, so the total length is del x in this x-axis. So half of this length will be half into del x. Similarly, the left side will be the same half into del x. So also we have meant that the positive x direction is this, as we have mentioned by this arrow. And this is the west wall, and the pressure that is acting at the west wall is equal to, we know that this is the center of this element. So there the pressure is taken as P. So there will be a change in pressure with respect to x-axis. That's why we have written that dou P by dou x mentions that change in pressure with respect to x-axis. To what extent, that is this 1 by 2 into x. That is the distance that we have mentioned here. And the minus sign is given here because it is in the left hand side. We have given the positive x is in this direction. So this wall is in this negative direction. That's why we have written the pressure minus the change in pressure in the particular distance of del x. So similarly, if you see the pressure at the wall in the east side, so we can write the same as the pressure plus dou P by dou x, that is change in pressure with respect to x-axis. And this is the quantity of the length, and half into del x is the distance that we are having here. Here we have put plus instead of minus because it is in the positive direction. So now we have to write down the mass flux in and out of the fluid element. We know that mass flux is the mass flow rate per unit area. So we know the formula for mass flow rate, that is rho a v. So if it is mass flux, we have to divide the area from that. So we will be getting rho into v. So density into velocity gives the mass flux. So let's write down the mass flux from this element's perspective. At the center, the mass flux is denoted as rho into u, that is density into velocity. So we are considering only this west wall. So since the direction is in the negative side, I have given the negative symbol. Change in this rho u by del x into the distance half del x, as we have did in the pressure case in the previous step. So this will be the mass flux in the left side. Similarly, what will be the mass flux in the right hand side? The same thing will be there except the symbol. So since the mass flow at the center is assumed as rho u, and at the right hand side it will be in a positive direction, so that we have to write rho u plus change in mass flux in the distance of del x. So similarly, if you see for another axis, that y axis, the only change that we have to make is instead of u stands for x axis velocity and v stands for y axis velocity. So the v should be changed and the axis is also changed. Here the rho v is taken as the velocity at the center, and at the wall, and at this particular wall, since it is in negative direction, we have given the minus sign, and change in rho v by del y, change in mass flux along this del y into the distance, that is half del y. Similarly, the outflow from this element should be the same except the negative sign, that should be changed as positive sign. Similarly, for the z-axis, instead of u and v, the velocity component is mentioned as w, and the axis should be changed as z. Similarly, at the outside, so at the inside we have the negative sign, and at the outside we have the positive sign, as we have did before. So these are the terms that we have for mass fluxes. So now let us see the net mass flow rate into the element. So the difference between the mass flux and mass flow rate is the inclusion of the area, as we have discussed previously. So in order to mention the mass flow rate, we have to multiply the area to this mass flux. So mass flux in minus mass flux out along the x-axis, already we have this equation. This is the mass flux in and this is mass flux out. That should be multiplied by the area across it which is crossing. So this is the x-axis velocity. So this is the cross-sectional area. That is, we know the area of this cross-section. So this is del y and this is del z. So the cross-sectional area across which this x-axis flow is taking place is del y and del z. So that's why we have given that. So this is mass flux and this is the area. This is mass flux out and this is the area at the outlet. The same inlet and outlet area are the same here. Similarly, we are writing that for y direction in and y direction out. So y direction in, we have this equation. Let's plug in here, and y direction out, it plugged here. But here the area is different. So this is the cross section where the flow is taking place. So this is del x and this is del z. So del x into del z is the area, and this is the mass flux in that is mentioned here, and this is the mass flux out that is mentioned here. Similarly, we have to write for z-axis in, that is here, z-axis out, that is here. Similarly, the cross-section area of z-axis is del x and del y, that is mentioned here. So this is the net flow rate of mass into the fluid element. So let's write this in a continuous form. So now this equation can be simplified. If you multiply this negative sign into this, it will become minus rho u minus these things, minus this term. So already we have a plus rho u here. Here you will be having minus rho u. So these two things will be get cancelled. Similarly, this rho v minus this minus rho v, and this will get cancelled. Similarly, this rho w and this minus rho w will get cancelled. And also we have del x, del y, del z. If del x inside and del y and del z are outside, it can be multiplied. Similarly here, del y is inside, del x and del z are outside, it can be multiplied to form del x, del y, del z. Similarly here, we have del x and del y, and del z is inside. We can multiply that to form del x, del y, del z. So now it has been simplified. So the minus sign is put on the left hand side, and this is the x term, this is the y term, this is the z axis term. So now we can see these things in common. Del z, now we can see del x, del y, del z commonly in all these equations, and we can take that out. So now the equation is in its simplest form. Let us take this equation as equation number 2. Now let's go to the first equation that we have derived in the first slide. So now we are going to equate the equation number 1 and 2. So this is equation number 2, and this is the equation number 1 that we have derived for what? For a rate of increase of mass into the fluid element. So now what we are doing, the rate of increase of mass element is equated to the net rate of flow of mass into the fluid element. So we are doing that here. So if we equate these two things, these xy and z terms can be cancelled out, and this dou rho by dou t term can be brought to the left hand side. If you multiply this minus into all these things, all the terms will become minus. Similarly, the dou rho by dou t term, when it goes to the left hand side, that will also get the minus sign. So everything can be multiplied by minus, and can be written in a positive. So this is the 3D continuity equation for unsteady compressible flow. So if the flow is compressible, the density will change. That's why we have included the density term inside the continuity equation. So if the flow is incompressible, we need not to include the change in density. So the density becomes constant. The density change in density with respect to time will become 0, and we can neglect that term. And this is the equation for incompressible and steady flows. This is the 3-dimensional equation. If you want to have only 2-dimensional, we can neglect this z. Sorry, this is dou w. So for a simple equation which is having only 2-dimensional, we can use only dou u by dou x plus dou v by dou y is equal to 0. This dou w by dou z need not to be included for 2-dimensional flow. I hope this video helped you to understand this 3-dimensional continuity equation. If you have any doubts, please drop me a comment. Thank you.